In this example, we're looking to compare two different populations that it wouldn't be fair to compare them directly. So anytime you have two different populations that otherwise could not be compared, we can compare them using what we call z-score. So with z-score, looking at these examples, what you'll notice is trying to identify two different populations that we wish to compare using the z-score. Okay, so z-score has a formula that we'll discuss here. Looking at example 1, the mean height of 20-plus-year-old males, okay, is 69.1 inches with standard deviation of 2.8. The mean height of 20-plus-year-old females, so I want you to kind of notice we're identifying two different populations, is 63.7 inches with a standard deviation of 2.7. NBA star Kevin Garnett is 83 inches tall. Now notice what we did in the problem. In the male population, we actually gathered an individual of interest, And in the population z-score formula, the letter X, that represents the individual value of interest. WNBA star Candace Parker is 76 inches tall. We did the same thing here. Notice we identified a specific person of interest in the female population. Likewise, here we have X for the female population. Who is relatively taller? That's the question. So what that means is we're not looking to see who's taller directly, because I can compare 83, 76, and see who's taller from there. The idea is we want to know, is Kevin Garnett taller more so than the average male than Candace Parker is to the average female? We want to know who is taller relatively speaking. So this is what we have. We have two populations. We're going to assume that we have a bell curve for both, okay? And anytime you have symmetry, once again, we are centered around the mean. Suppose this first population, let's call that the male population. Let's call it capital M. And this one here, we'll call it capital W for the women. The male population has a mean, we're centered on the mean, 69.1. We'll make a note of the spread. Standard deviation is equal to 2.8. Likewise, we have some information on the female population as well. Here we have women on average are 63.7 inches tall. We'll make a note of the spread. The standard deviation is 2.7. Okay. So again, it wouldn't be fair. It wouldn't be fair to compare these two populations directly because they both have different statistics. They both have different statistics or parameters. So what we would like to do, since we cannot compare these two directly, is we're going to reset the board. Okay. And if you're looking at the handout, there are solutions at the end of it. Okay. It's doing the same thing. We're resetting the board. That resetting the board, we give it a name. It's called standardize. Okay. We standardize both populations into a single bell curve, and we give this bell curve a special name, the standard normal curve, Z. Okay. And according to the handout, Z, anytime we standardize to Z, you're always centered around the mean, but the mean always for Z will be 0. The standard deviation always for Z is 1. Okay, so that's the first thing we want to do when it comes to the two populations. We want to reset the board into Z. Now, the question is, who is relatively taller? We still want to know who's relatively taller between the two unique individuals of interest. So that means z-score. When we're dealing with this bell curve Z here, I need to place some pieces on the board, z-scores. So we're going to use a formula, Z equals X minus mu over sigma. And we'll do that for the male population. And we'll also do Z equals X minus mu over sigma for the female population, okay? So X, once again, will represent the individual value of interest. So here, let me pull up a calculator. Okay. Let's get this going, 1 sec. Okay. So the formula is X minus mu in the numerator, sigma in the denominator. So let me go ahead and start off with X minus mu first. In the problem, X is the individual of interest, and we denoted in the male population, Kevin Garnett is the individual of interest. He is 83 inches tall. Then we subtract the population mean. Here, notice on the bell curve, our population mean is there, 69.1. And we divide by the spread. Our spread here is 2.8. Okay, and that'll give us a number. Let's call this 4.96. And we'll make a note of that in 1 sec. We'll do the same thing for the female population. We need to take female parameter and individual value of interest and apply the same formula. So Candace Parker, let's see how tall she is. Candace Parker is 76 inches tall, so that's X. So we do 76 minus, we need the population mean for the women, 63.7, and then we'll divide by the spread. Okay, so here we have 2.7, and we'll get a number. Okay, let's call it 4.56. Okay. Now, we still haven't answered the question, who is relatively taller, but at least now we have something to compare. We have 4.96 to compare, and we have 4.56 to compare. So this horizontal axis on the Z, think about that like a number line, okay? This number line is centered at 0, and I would like to place these pieces of the board onto the Z curve. So if the horizontal axis is a number line, both my numbers are positive. They should go maybe somewhere here, okay? If they were negative, they would go on the other side of the number line, but 4.56 goes here, 4.96 goes here. And the question is, who is relatively taller? We compare the two values, okay? Taller, in terms of numeric, means the bigger number, okay? That person will be relatively taller with respect to their population. So 4.96 is the bigger number than the 4.56. And 4.96 came from this population here. So when the question asks, who is relatively taller, we conclude that Kevin Garnett is relatively taller. What that means is, notice, on the Z curve, on a bell curve, this is the mean, this is average, right? Both the individuals are actually taller than average. The question is, though, who is relatively taller between the two? Although both are taller than their respective population, Kevin Garnett is actually the taller out of the two, relatively speaking.